All right, strap in, everyone. We're going deep into quantum repeaters today.
Yeah, these things are pretty wild, huh?
That's an understatement. But thankfully, we've got Yurgo Schneppat's essay to guide us. So, to start, what exactly are these quantum repeaters, and why should we care?
Well, they're kind of like the missing link for quantum communication, which, as Schneppat points out, has the potential to completely revolutionize how we communicate and compute. Imagine a world with unbreakable security systems and a global quantum internet.
Hold on, a quantum internet? That sounds like something straight out of Star Trek.
I know, right? But it's a real possibility, and quantum repeaters are key to making it happen. You see, quantum information is incredibly fragile and difficult to send over long distances.
Why is that? I mean, we can send regular information all over the world through fiber-optic cables, right? What makes quantum information so different?
It all comes down to the bizarre rules of quantum mechanics. Schneppat does a great job explaining this in his essay. We're talking about things like superposition and entanglement.
Right. Superposition is where a quantum system can be in multiple states at once, and entanglement is like two particles linked no matter how far apart they are. But how do those things make it hard to send quantum information?
Well, think of it like this. Quantum information is encoded in these delicate quantum states, like superposition and entanglement. But these states are incredibly susceptible to noise and disturbance.
So like trying to send a whisper across a crowded room, it's bound to get lost in all the chatter.
Exactly. And the further you try to send that whisper, the more likely it is to get garbled. It's the same with quantum information. The longer the distance, the more noise and loss it encounters, leading to something called decoherence.
Decoherence, that's where the quantum state collapses and we lose the information.
Exactly. It's like our whisper turning into meaningless noise. And that's where quantum repeaters come in. They act as a sort of relay station, helping to extend the range of quantum communication.
So they boost the signal, making it stronger and less susceptible to noise.
It's not quite that simple. Schneppat explains that instead of boosting the signal, they actually break the communication down into smaller, more manageable segments.
Oh, I see. So instead of trying to send the entire message at once, we break it up into smaller chunks and send them one at a time.
Exactly. And each repeater station, the quantum information is carefully purified and amplified, removing some of the noise and decoherence it has accumulated.
And that's how we can extend the distance over which we can send quantum information.
Exactly. It's like creating a chain of whispers, where each person only needs to whisper to the next person in line, ensuring the message gets across the room without getting lost in the noise.
That's pretty clever. But how did these repeaters actually work? What's going on inside those relay stations?
Well, it gets a little technical here. Schneppat describes how repeaters use a process called entanglement swapping, which involves entangling particles at each station, and then cleverly connecting those entangled pairs to extend the entanglement across the entire distance.
Entanglement swapping. That sounds pretty mind-bending.
It is, but it's also incredibly ingenious. It's like creating a chain of entangled links, connecting the sender and receiver through a series of intermediate nodes.
Okay, I'm starting to get the picture. But entanglement swapping aside, what are some of the key technologies that make these repeaters possible? Schneppat mentions things like quantum memories and photonic interfaces.
Right, those are essential components. Think of quantum memories as temporary storage units for quantum information. They hold on to those delicate quantum states until they're needed for the next step in the chain.
Like a quantum hard drive.
Exactly. And then there are photonic interfaces, which convert the quantum information from the memory into light particles or photons, so it can be sent down the fiber optic cables.
So like a translator between the quantum world and the world of light.
Exactly. And of course, you need detectors at the other end to measure those photons and extract the quantum information.
Sounds like a delicate and complex process.
Oh, it definitely is. And Schneppat doesn't shy away from the challenges involved. He talks about the need for incredibly precise control over these quantum systems and the difficulty of maintaining entanglement over long distances.
So while the potential of quantum repeaters is huge, the technical hurdles are pretty significant.
Absolutely. But the progress being made in this field is remarkable. Researchers around the world are working tirelessly to overcome these challenges and bring the vision of a quantum internet closer to reality.
So it sounds like we've got a long way to go, but the journey is well underway.
That's right. And the potential rewards are so vast that it's definitely a journey worth taking.
All right, so we've laid the groundwork for how these quantum repeaters work, these amazing little devices. But let's get down to brass tacks. What can we actually do with them? Schneppat lays out some pretty exciting possibilities, right?
Yeah, he really does. One of the biggest ones is quantum cryptography.
Okay, so cryptography, that's like keeping secrets safe, right? I mean, we already use encryption to protect our online data, so what's so special about quantum cryptography?
Well, as Schneppert explains, quantum cryptography takes security to a whole new level. It uses the principles of quantum mechanics to create unbreakable encryption keys.
Unbreakable. Come on, nothing's truly unbreakable, right? Some hacker out there has got to be able to crack it.
Well, in theory, quantum cryptography is indeed unbreakable. Schneppert really digs into this. It all comes down to the fact that any attempt to eavesdrop on a quantum communication channel will inevitably disturb the delicate quantum states, leaving behind detectable traces.
So, like, if someone tries to snoop, we'll know immediately. It's like having a built-in alarm system for our secrets.
Exactly. And this is huge because right now, our best encryption methods are based on math problems that are really hard to solve, but not impossible. With enough computing power or even just a clever algorithm, they could be cracked. But quantum cryptography relies on the fundamental laws of physics, not just complicated math.
So even with the most powerful supercomputers, our secrets would still be safe.
In theory, yes. Schneppert seems pretty confident about that. And this could have massive implications for, well, pretty much everything that requires secure communication. Think finance, government, military, healthcare, you name it.
Wow, yeah, that's a big deal. Okay, so unbreakable security. What else does Schneppert have in store for us? He mentioned something about quantum cloud computing, right?
Yeah, that's another mind-blowing application. Imagine being able to access incredibly powerful quantum computers from anywhere in the world, just like you access cloud services today.
So instead of needing your own massive, expensive quantum computer, you could just rent processing time on a quantum cloud.
Exactly. It would democratize access to this incredibly powerful technology. Schneppert points out that researchers, businesses, even individuals could potentially use it to solve complex problems that are simply beyond the reach of classical computers today.
Okay, starting to see a pattern here. Everything quantum is just like exponentially more powerful. What about this secure data storage for the future thing Schneppert mentions?
Oh yeah, that's where things get really futuristic. Schneppert suggests that quantum encryption could be used to create data vaults that would remain secure for, well, essentially forever.
Forever. How is that even possible? I mean, technology changes so rapidly, anything we build today is probably going to be obsolete in a few years, right?
True, but Schneppert argues that this is different. With quantum encryption, the security guarantee comes from the laws of physics, not the technology itself. So as long as those laws hold true, the data should remain secure, even if the hardware becomes outdated.
So it's like we could store secrets today that our great-great-grandchildren could still access safely centuries from now.
That's the idea. And Schneppert suggests it could have profound implications for everything from preserving historical records to safeguarding sensitive information for future generations.
Okay, we've covered cryptography, cloud computing, data storage. It's a lot to take in, honestly. Is that everything?
Well, not quite. Schneppert saves the best for last. Remember that quantum internet we talked about earlier? Well, he actually lays out a vision for how we could use quantum repeaters to create a global network of interconnected quantum computers.
A quantum internet, like a real working quantum internet, not just a theoretical concept.
Exactly. And Schneppert argues it could revolutionize pretty much every aspect of our lives. Think instant, secure communication across vast distances, unhackable financial transactions, global collaborations on scientific research, maybe even teleportation, who knows?
Teleportation. Okay, now you're just messing with me. But seriously, a global quantum internet. That sounds like something straight out of a science fiction novel.
I know, right? But Schneppert presents a pretty compelling argument for why it's not only possible, but potentially inevitable. And the key to making it happen, you guessed it, is quantum repeaters.
So these repeaters are not just some cool gadget. They're potentially the foundation for a whole new era of technology.
That's exactly what Schneppert is saying, and it's pretty exciting, isn't it?
Yeah, exciting and a little terrifying, honestly. But, before we get too carried away, I think it's important to acknowledge that all of this is still very much in the early stages. Schneppert himself admits that there are huge challenges to overcome.
Oh, absolutely. Building a quantum internet is a monumental task, both technically and logistically.
Like we're talking engineering marvels and global cooperation on a scale we've never seen before, right?
Exactly. And that's why Schneppert emphasizes the need for continued research, development, and investment in this field.
So, while the potential is enormous, we need to be realistic about the timeline. We're probably not going to be browsing the quantum web next week.
Probably not, but who knows, maybe sooner than we think. There's a lot of brilliant minds working on this, and progress is happening rapidly.
Well, that's encouraging. So where do we go from here? What's the next step on this journey towards a quantum future?
Well, that's what we'll explore in the final part of our deep dive. We'll delve into the current state of research and development, the challenges that lie ahead, and the potential timeline for when we might actually see some of these amazing applications become a reality.
Okay, so we've talked about the amazing potential of quantum repeaters, but where do we stand right now? Are these things just a pipe dream, or are people actually building them?
Well, as Schneppat makes clear, we're not quite at the quantum internet stage yet, but there's a lot of exciting research and development happening right now. It's kind of like, the early days of the internet where people had this vision of a connected world, but the technology was still in its infancy.
So, lots of potential, but still early days. But Schneppat does mention some actual projects, right? Like real-world efforts to build these quantum repeaters.
Yeah, definitely. He highlights work being done with all sorts of different technologies. There's trapped ions, where you use lasers to control these individual atoms, and there's superconducting circuits, which operate at super low temperatures, almost absolute zero. And then you have solid-state systems like diamond defects, which use tiny imperfections in diamonds to store quantum information.
Wow, that's a lot of different approaches. It sounds like everyone's trying to figure out the best way to build these things.
Yeah.
So is there a clear winner, like one technology that's pulling ahead of the pack?
It's tough to say right now. Schneppat points out that each technology has its own strengths and weaknesses. Like, some are better suited for long-distance communication, while others are more compact and easier to scale up.
So it's like a quantum race, with everyone vying for the lead.
Yeah, I guess you could say that, but it's a race where everyone benefits from each other's progress. Like, new discoveries in one area often lead to breakthroughs in another. Schneppat describes this really well in his essay.
So lots of competition, but also lots of collaboration. That's kind of cool. But Schneppat also mentions the economic and infrastructure challenges. Like, building a quantum internet is going to take a lot of money and resources, right? Is there enough support out there to make this happen?
That's a good question, and Schneppat doesn't shy away from it. He argues that, we need a sustained commitment from governments, businesses, and research institutions around the world. But the good news is that commitment seems to be growing. We're seeing more and more investment in quantum technologies.
So people are recognizing the potential, and the money's starting to flow. But I guess the big question is this something we really need? Like, is a quantum internet just a cool idea, or is it essential for the future?
Well, Schneppat definitely leans towards the essential side of things. He points out how vulnerable our current internet is, especially with the rise of quantum computers that could crack our current encryption. A quantum internet with its unbreakable security could be crucial for protecting our data, our privacy, and even our national security.
So it's not just about faster communication or more powerful computing. It's about building a more secure and resilient digital infrastructure for the future.
Exactly. Schneppat lays out a pretty convincing case for that.
Well, this has been a fascinating deep dive, and I gotta say, Schneppat's essay really got me thinking. It's amazing to consider the potential of quantum repeaters and the incredible future they might unlock.
Yeah, it's pretty mind-blowing stuff. It makes you wonder, what kind of world will we create with this technology?
That's a question for all of us to ponder. A big thank you to Jorgo Schneppat for laying out this fascinating roadmap to the quantum future. And to our listeners, keep exploring, keep questioning, and keep pushing the boundaries of what's possible. Who knows, maybe one of you will be the ones to make this quantum dream a reality.